take a few moments to finish up your pre-work. Again, remind you that the on your owns are in the book. So if you don't get through it all, or even after I explain it here, if you still have some questions, you can go back and review their layout, their setup, and then I encourage you to come back to me with questions you might have. Okay. Also, the plan is still for me to do tutoring on Mondays. That's what I did last year. Usually meet in here about 10 minutes after school ends and spend between a half an hour to an hour in here answering your questions, but I need you to come with questions. Tutoring isn't so that I can repeat stuff that I choose is important, though that may happen at times, but usually it's based upon your questions. And I might go back a little farther and review some things that you weren't really directly asking, but if I understand that your question is based upon prior knowledge that you don't have, like something else that you should have understood beforehand, I'll go back to that and try to fill in some gaps for you. But both in class and in tutoring, I don't know what you don't know unless you speak up. So I really do need you to help me. I am looking at the nonverbal feedback, so when I see the face that goes, you know, that may cause me to repeat something or a few other things. But other than that, again, if you give me the impression you're getting it, like it's okay, we'll keep on moving. And if I ever ask for bobbleheads, that's when I need you to just forget about being embarrassed in front of your friends and say, it's yes, it's no. I just need something, like no, I don't get it, or yes, I get it. We're not going to do hula dancer, right? Be like in the car, little wiggly thing on the dash. That's not, no. Just bobble heads, not bobble bodies. We're a Christian school after all. We don't bobble bodies, do we? All right. On your own, 1.9. For now, I'll leave the screen down. As I said before, when we start doing some live work, when I'm actually up here with whiteboard markers and we're doing stuff, the screen will usually be up, but this does help a little bit, I think, on the video. So when it's predominantly PowerPoint, we'll just stick with the screen down for now. So on your own, 1.9. What's the first thing I'm going to write on my paper? Every time, not the specific answer. Every time I have a question like this, I'm going to start by writing down just known and unknown. Known and unknown, because you're answering a question, right? Now, right now, your known is maybe one fact. Later on, the known might have 10 pieces of information in it. When you have a formula like an ideal gas law, and there are multiple variables, you're going to want to know, you're going to write down all the known. You're going to look into that word problem and pull out all the pieces of information that you can use to reconstruct or to construct your solution. So everything that's known. Now, part of science is trying to figure out what is necessary and what's unnecessary. If I'm in this room and I'm doing an experiment, there's a lot of information that might be true that I could write down. It may not all be useful. It could be true. So part of science is also to uncover what you need, but limit it to what you need, right? I mean, I'm doing an experiment on that side of the room. The fact that the computer is on is true. Do I really think it affects my experiment? If it doesn't, I don't need to keep that information. You know, I'm doing an experiment, my body temperature may not matter. Other experiments, it may. So part of science is being able to figure out what is necessary to know and what's unnecessary to know. We're surrounded by bazillions of pieces of facts. We don't use them all. Here it's pretty simple. The problem gives you something and asks you for something else. So write down your known and your unknown. The known is the time, right? 0.00555 hours. You can hold your breath that long. Should we be impressed? We find out not really, right? Because we're asked, how long is that in seconds? And they give you that. They help you out a bit. Say, convert it to seconds. Because you're not used to thinking about holding your breath in terms of hours, because the scale is too big, right? I held my breath for 2. 2 what, hours? No, 2 Smurfs, right? No, we don't think in terms of hours. We may think in terms of minutes. If I said I held my breath for 1.5, you might think minutes. You probably wouldn't think hours. You probably wouldn't think seconds either, because that's kind of short, like, oh, man, I can't hold my breath anymore. Okay, so we usually think in terms of minutes, but they tell us here, let's see if we're impressed or not by converting it to seconds. So I've got my known and my unknown, now what? You can answer back, don't worry about hands right now, that's fine. Statements of equality, right? Because I know I need to turn it into something useful. And I'm going to do that with 2 of them. I need to relate, ultimately I need to relate hours to seconds, right? If I knew a statement of equality, if I knew that 1 hour is 3,600 seconds, which I do know, then I could do it as one step. If you don't know that, then you have to take it in 2 steps. Well, I do know, we're pretty comfortable that an hour is 60 minutes, not base 10, which means it messes up our math, right? We can't just simply move decimal points. We got to multiply and divide by 60. And also a minute is 60 seconds. Who came up with this crazy system? Anyway, so 1 hour is 60 minutes, 1 minute is 60 seconds. You see right now that you're going to have a 2-step conversion factor, right? 2 conversion factors in series. So we write down our known times our 2 conversion factors. Hours times minutes per hour, that's going to put me in the language of what? Language of minutes, good. Hours times minutes per hour puts me in the language of minutes. Now the next conversion factor, seconds per minute, changes me from the language of minutes into the language of seconds. Doing the math, my given number of hours times 60 divided by 1 times 1, okay, we don't worry about the ones. And technically, if you look in the book, it says take your known and put it over 1. That's what this is. It's just over 1. I don't bother with the over 1 because that's obvious. What's 7? 7 over 1. What's 10? 10 over 1. But it's all over 1, so it's over itself. Here we keep it because units are involved. Something over 1 is just itself. So if I knew that 60 times 60 is 3,600, I could have it be 3,600 seconds per hour and do it as a 1-step conversion. But this is using the 2-step conversion. So any questions on the setup for this? Everybody comfortable with that? A little bit of a bobble? Okay. 110, same setup. My known, 0.0091 kiloliters. Asked for volume in cubic centimeters. Statements of equality. You see there's a process here, right? If in doubt, you're looking at a problem going, oh, I'm really bad at tests. I have no clue what to do. What should I do first? Write down known, unknown, statements of equality. Okay, I just gave myself a hint because I knew the process. Now I'll go back and I'll look for all the known. And if I'm not sure what to select out of it, I'm going to write down everything they give me that's useful. Later on, there may be formulas that we need that are known. They're just common knowledge formulas. I can add that to my known. Or on your process, you might have a separate space like I do for equations. And then we're going to bring that all together in the end to solve the problem. So my statements of equality, do I know something, first of all, that's going to help me get from, well, kiloliters, I can put that in the language of liters. Yes, ma'am?
I don't know if this really matters, but I was wondering, when it says like the centimeters cubed, volume equals, isn't meters distance? So does it matter if you put like distance equals?
Cubic is a volume.
Okay.
So it's a centimeter. If it was a centimeter, it'd be a distance. But it's a cubic centimeter, which is a distance times a distance times a distance, which is a volume. It's, okay? It looks like if it were just centimeters, it would be a distance unit. Centimeters cubed is a volume unit. Okay? Yes, sir?
Is centimeters squared still a distance?
No, that's an area. Okay, so if you're looking at how far is it from here to that side, that's a distance. If I say how many square feet of floor tile do I need, it's this length times this length. If I say how much air can I put in this room, it's this length times this length times this length. See, so it takes us from distance to area to volume. And then we go into the 4th dimension, which is time, and then the 5th dimension, and it gets all wacky after that. So we're not going to go there for this class. We'll do that in physics, maybe. So another thing, too, you guys all aced the vocabulary part of the quiz. The tables below, that's where a lot of you struggled, and I put that on there so you would know. You need to memorize that, too. I didn't grade that as the quiz. I included that. But kilo is a lowercase, and liters are an uppercase. A lot of you dropped the lowercase l. You made it a lowercase l, or used uppercase k. So remember, the kilo, the centa, the milli, those are all lowercase prefixes. And all of the other base units are lowercase, except for the liters. Liters is a capital L. It matters. And again, that's why I changed the font, too. It matters. The old font I had would have just had that as look like a lowercase l, and I couldn't do that to you. So get in that habit. So I can convert from the language of kiloliters to the language of liters, but am I asked for the language of liters? I'm asked for cubic centimeters, still volume. Now I do know that 1 liter is a milliliter, or 1 milliliter is 1/1000th of a liter, excuse me. But yesterday we learned the secondary Rosetta Stone, didn't we? That 1 milliliter is a cubic centimeter. You're going to use this thing over and over and over again, so look to use it. I'm going from a volume to from liters to what looks like a distance unit, but it's not, it's a volume unit. What's the magic trick to convert from one to the other? It's going to be this relationship right here. 1 milliliter is equal to 1 cubic centimeter. So, think about it. Do I actually need to convert from kiloliters to cubic centimeters? Or could I just convert from kiloliters to milliliters and then use the same number but change the units from milliliters to cubic centimeters? See? And that's what I did here. A kiloliter times liters per kiloliter times milliliters per liter. See that? And my answer then is 9,100 milliliters. Was I asked for milliliters? No. I was asked for cubic centimeters. Ta-da! Cubic centimeter and a milliliter are the same thing. So I just take my unit, my coefficient, 9,100 milliliters, and I change it to be 9,100 cubic centimeters. I don't need to do the 1 divided by 1, right? We would have one more conversion factor. We would daisy chain 3 of them in series. This would have put us in the language of liters. This would put us in the language of milliliters times 1 cubic centimeter over 1 milliliter. See? And all we would do then is translate from the language of milliliters to the language of cubic centimeters, but we don't need to do that technically because it's a 1 divided by 1, which is 1. All we're doing is changing the units. So if you need to go to cubic centimeters, or going from cubic centimeters to milliliters, go to that unit, milliliters or cubic centimeters, and then just change the unit because they're the same value. Cubic centimeters and milliliters. Oh, we've got one more. I was all excited about 10. Let's go on to 11. 32 square meters. See? Area. Area. Square meters. Distance times distance is area. Distance times distance times distance is volume. And unknown is the same area in square millimeters. Looking up here, we see that the units go, they're both equal, right? Our answer is going to be equal to our given, our known. Stop for a second and say, okay, my units are going from meters to millimeters. I'm going from a larger unit to a much smaller unit. So my coefficient must go from a small number to a much bigger number. My number has to become much bigger to compensate for the units which are much smaller, if they're equal. So we're looking for a big number compared to 32 because millimeters are a small number compared to meters. And the fact that it's squared means it's going to be even bigger. So here we go. Statements of equality. A millimeter is 1/1000th of a meter. And we just plug that in. Now here's the trick. I could have 32 meters squared times 1 millimeter divided by 1/1000th of a meter times 1 millimeter over 1/1000th of a meter. We have to include it twice, right? Because it's squared. If I use the conversion factor once, it's only going to count for one of those meters. I have to use it twice to account for the squared units. Yes, sir?
When I did it, I converted meters to centimeters, and I converted centimeters to millimeters, and I still got the same answer.
It's possible.
Okay.
Yeah, it's true. It's a lot more work, but it's true. And that's why I'm saying these are processes, but there is often multiple paths to the right answer. The problem is the more steps you give yourself, they might all be true, but every step brings with it the potential of making an error. And once you make the error, it carries through. That's one of the reasons as well why it takes so long for me to grade your work sometimes, is when you make a mistake, it doesn't mean everything after that point is wrong. I take your error and I walk it through the entire problem. See? So, I'll give you an example. At the Naval Academy, I had a 3-hour celestial navigation exam. I was about 2 hours and 10 minutes into it when I realized that my first plot point was wrong. And I had to go back and rework what I'd taken 2 hours to do. I had to rework it in 50 minutes. And the exam was not it was just say, did you get to the right spot at the end or not? Well, I could not get to the right spot at the end because I made an error on the first step, and I think I made the correct choice for every, 10 steps after that. But I would not have ended up in the right place. So I had to go back, start all over, and work the whole thing. I don't do that to you. I say, if you're on step 1 and you get a wrong answer, okay, that's partly wrong, but is your second part right given that I assume your first part was right? Is your third part right given that the second part is right? See, and I kind of walk it through. So missing the first step of a 10-step process doesn't mean you just lost all 10 steps. It means you missed one step. But if your process is right after that, I'll give you credit for knowing process and using your error correctly. So in that case, what you did was fine. You did more steps than necessary, which meant you could have potentially introduced more error. Okay? But here it's just the fact that the units are squared, which means you need to use the conversion factor twice to compensate for the square. Millimeters over meters wouldn't have done it. Millimeters squared over meter squared does it. Which means, remember when you do the math here, it's 1 times 1, which would be 1. And down here you've got 1 1,000th times 1 1,000th. Makes the denominator very, very small, which means my answer is going to be very, very big. I'm dividing by a very small number, which means the answer blows up. If the denominator is really large, the result is very small. If the denominator is very small, the division makes my answer very large. And that's a good check for you. Like I said, if we're converting from a larger unit to a much smaller unit, then the coefficient has to correspondingly become much bigger. Hopefully you agree that 32 million is much bigger than 32. Okay? And we can say 32 meters squared is equal to 32 million millimeters squared. Because if we were doing the square foot, or the area of this room for floor tile again, it's more likely we're going to measure it in meters, not millimeters, or micrometers. And make it even bigger. We'd blow it up even more. But we don't do that. So hopefully that helps you in your setup, and it helps you with your homework, and helps you with all upcoming work. We're going to need our books for a little bit here on page 19. And we talk about making measurements. A real quick, let me get my keys here. I need to actually get a graduated cylinder for the second part of this, so bear with me for just a moment. Go ahead and take a look at that ruler in your book. It's measuring like a blue line, probably supposed to represent a piece of yarn or something like that. Here we go, it's graduated cylinder. Okay. So something to consider. I've kind of taken this section, I've condensed it down. Remember, you should be doing your own reading as well, so you should have read up through at least through this point in the book by now. If not, catch up. Try to be a day ahead of the class so that when I cover it in class, it's not the first time you're hearing it. All right, so making measurements, distance measurements, and let's just talk about a ruler as an example. These are principles that you'll apply in multiple different ways as we go through the course and through the rest of your life, frankly. Some of these I use anytime I do fine woodworking. My fine woodworking and other people's fine woodworking aren't the same thing. Mine's not so fine, okay? Sometimes I'm more like a framing carpenter, right? When framers cut something and it's a little bit too short, they just nail it anyway. They leave the gap, they put a wedge in there, it's kind of rough. Fine carpentry, it's like, okay, how thick is my blade? Because it matters, right? It's not enough to cut the line. Do I cut on the line? Do I leave the line? Do I take the line? The kind of conversations my dad and I'd have. He'd mark something, say, here, take the line. Or here, leave the line. Meant he drew the line and then he realized, oh, if I take the line, this wood's going to be one blade thickness too short. So leave the line because that little bit matters. That's kind of principle here because we want to be as accurate and as precise as possible. And those are two different things, and we'll cover that today. So notice in the book that they start the measurement here at the 1 inch mark. Why don't they take it all the way to the end, to the 0 mark? What do you think? Well, practically speaking, where is your ruler going to find wear and tear? Where is it going to be changed because, oh, if you're handing it off and you drop it? Does the middle of the ruler tend to get marked and dinged up, or do the ends? The ends, if any corner is going to be chipped or nicked, it's, by our luck, it's going to be on the top where the scale is and all the way to the left where the 0 mark is, and your ruler gets a ding in it and bends the 0 point, what happens to every measurement after that? They're all off, right? So technique is start at the 1. Start at the 1 when you measure. Since that's the technique, what is the most common error that students make when making measurements? Forgetting to take the 1 off, right? You're not starting at 0, you're starting at 1. So if I start at 1 and I end at 2, how long is my piece? It's only 1 inch long, right? But you will write down 2 because it landed on the 2, and you're used to starting at 0. So technique-wise, if you start at the 1, make your measure, make sure you subtract 1 from whatever you read on the scale, right? And we're starting, same thing with the fine carpentry. You notice on tape measures, at the end they got that little hook, the hook's on the wood. Is that thing firm or loose? It's always loose and jiggly, right? That's your error. That you need to account for that kind of an error in your measurements. So doing fine carpentry, you don't just, framing carpentry, just hook it, pull it, 12 feet, mark it, cut it. Fine carpentry, you're going to move and make sure you have a more precise measurement than that, because that jiggle space matters. And in science, when we're trying to do a quantitative measurement as precise as possible, it matters. So starting at the 1 inch mark, next point, note the scale. If you're using an English system ruler, your ruler is probably marked off in 1/8 or 1/16. Probably not 1/4 inches, but 1/8 or 1/16, right? So if you look at your scale and say every mark is a 1/16 of an inch, after you note the scale, then read your piece that you're measuring to that scale. If it ends on 2 1/8, and I've added that, and I take that 1 off, okay, my piece is 1 1/8 long. If it ends exactly on the 1/8 mark. Here's the rub. Seldom, unless you've cut it that way, do things end precisely on a mark. They're going to end somewhere in the middle. So what we do is we take that last mark. Let's say our piece is a little bit longer than the 1/8 tick mark between the inch marks. It's a little bit longer than the 1/8. So we know that it's more than an 1/8, right? It's an 1/8 plus something. How much? Well, if every mark is an 1/8, and this piece is exactly between 2 marks, how long is the additional piece? A 1/16, right? So how long is my piece? I've got to add a 1/16 to it. You see? Here's the deal with measurements. You're expected to measure it to the closest mark, and then you're expected to estimate it to where it lands between the marks. Now, this gets confusing in English because I just said if it's marked every 1/8, potentially if it's halfway, it's a 1/16. If it's a 1/4 of the way, it's a 32nd. Okay, and so you need to do that. You need to add a 32nd to the measurement with the 1/8. And you got to get common denominators and add them, and then simplify the fractions and all that kind of stuff. Okay, so English kind of gets messy. What happens in metric when we use a metric ruler? It's all tenths, right? It makes sense. Oh, it's exactly on this mark. It's exactly, let's say that between our 1 and our 2, everything is marked off in tenths. It's exactly on this tick mark. Okay, it's 1.4. Next one is 1.5. Oh, between the two, what are they? Is it halfway? Yeah, okay, so it's 1.45. It's exactly halfway. Oh, I think it's a 1/4 of the way. Okay, it's 1.425, or 4.3. We make those estimations. So whenever we have a ruler, whenever we have this device, we're going to be working most dominantly in metric. And most dominantly, you look at the scale, you find out what the scale is. It's usually going to be marked to the 10th, which means you're expected to estimate it to the 100th. You've got to go one more place. Read between the marks, and you figure out what percentage it is between the two and add that decimal place. So rather than it being 1.1, and you see it's between the 1.1 and the 1.2, you would need to estimate. I see that as a 1.13. Why? Because a 1.1 is given to me, and a 1.2 is given to me, and this thing I'm measuring is between the two, and it's about 20% of the way, or 30% of the way. So it's 1.13. Okay? Take it to the scale the device is designed for, and go one more decimal place. Now for liquids, they use the graduated cylinder as the example. This is a graduated cylinder, and they show you what's called the meniscus. Let me turn the page over there on the bottom of page 20. the meniscus. I'm not going to fill it with water now, but when you put water or fluids into a graduated cylinder, you're going to see this phenomenon where rather than the water being nice and level, it's going to curve down from all directions. The center is going to be lower than the edges. And when you look at it from the side, you'll see the edge line, but you'll also see the bottom. It'll look like a little bit of a bow, just like they show in the book. A little bit of a bow that you see, okay? And you're going to measure the volume at the bottom of that bow, not at the top. Graduated cylinders are calibrated to account for the meniscus. It's a phenomenon where the sides adhere to the glass differently than the center. And so these things are calibrated that when I read this line, the measurement, I'm to read it at the bottom of the meniscus and I'll get the correct answer. If I read it at the top, I've overestimated or overmeasured how much is there. So always read at the bottom of the meniscus. Are there any questions on that? Pretty straightforward once you know that trick, right? Now, they also in there say look at the scale. In this case, there are 10 milliliters between these marks, or between these major measures, and there are 9 tick marks between. So every one is 1 milliliter. If I asked you to use this, and I told you that every tick mark was a milliliter, and I gave it to you to measure a volume, what should your answer be to me? In what place? If this reads millimeters, or milliliters, excuse me, then I would expect your answer to come to me in 1/10 of a milliliter. Because I could read this as 61, and I could read it as 62, but I have to estimate it as 61.4. See? So take it to what you could read it from here, absolutely, and then estimate the next decimal point. Accuracy and precision. This is going to be the death of us. So put on thinking caps, literally sometimes, and think with me through this issue of precision and accuracy. We're going to start with a concept, and we're going to move into application. And this is what I referred to previously when I said that if a measurement is written down as 2.5 or a measurement is written down as 2.50, it matters. We're going to discuss right now why that's significant. A couple of concepts. For vocabulary, these are in blue because they're in your book and you need to know these for vocabulary. That accuracy is an indication of how close a measurement is to the true or the correct value. How right is it? If you're doing a math problem and the answer is supposed to be 3 and you get 3, then you're right, you're accurate. Okay? Part of the problem is we don't always know what the right answer is. That's what we're trying to figure out. But ultimately, what you get as an answer and what the correct answer is, the difference is how accurate you are. So accuracy has to do with how close your measurement is to being the correct measurement. If I give you a block of metal and say, find the length of this block of metal, and I give you a ruler to do it, and I've already measured it with a much better piece of equipment than you have, and I know how long it is, I will take the answer you give me, compare it to what I know it to be, and the difference will tell me how accurate you are. So accuracy is how close to being correct you are. All right, that's accuracy. Precision, that's different. And precision is an indication of the scale on the measuring device that was used. If I give you a device that's designed to measure miles, and I ask you to measure the length of that desk, it's not like the appropriate instrument, is it? It's way too big. If I say, how much do you weigh? I don't know. Go stand on the metric ton scale, like at a dump yard or something like that. You stand on it, it barely even moves. It's like the scale doesn't even know I'm standing on it. It's not the right instrument. Your answer is going to be incredibly imprecise. But if I send you over to let's say a bathroom scale, that'll give you a more precise measurement. And if I send you over to some scale in a biolab that's designed to measure percent body fat, I mean, I can get a really accurate measure because I have a very precise instrument. I've got something that's designed to give me very, very, very precise. May not be accurate, but precise answers. We'll get into the difference in just a minute. So here's the deal. They often use this. Makes sense for the old archers in here, right, Starnes? Okay, let things fly down range. Here's the difference. If I'm discussing accuracy and precision, accuracy is how close I am to hitting the bullseye, because that's where I'm shooting for. I'm trying to accurately hit the bullseye. When I let an arrow go down range and I don't hit the bullseye, I'm being inaccurate. But when I hit the bullseye, I am being accurate. However, precision is my pattern, how tight my pattern is. Think of it that way. Here's the deal. We're going to argue that how accurate you are is based upon you, the operator. And how tight your pattern is more based upon the equipment you're using. Let's look at this for a second. Now, they're going to say that this pattern shows something that is not accurate and it's not precise. But let's actually go from the other side and work from greater to lesser. It's accurate and precise. How do I know that that bullseye all the way on the right over there, how does that show me that it's this pattern is very accurate? Everything's on the bullseye, right? Or at or close to the bullseye. It's very accurate because just about every arrow or every shot hit the bullseye. It was accurate. It got the right place. Okay? That's accuracy. It's hitting the target. It's also very precise because of what, ma'am?
Because all of them are like close.
Yeah, they're really close together. It's a tight pattern, and the tight pattern is over the bullseye. So that archer would be considered, or marksman would be considered both accurate and precise. Next to that, the next one over to the left, the second one, they're not accurate, but they are precise. So they're not accurate, meaning they're not hitting the bullseye. But they are precise because their pattern is tight. Okay? Now, if I make the argument that accuracy is the operator and precision is the equipment, what do I say? What would my generalization be about that second marksman right here? How good are they? But what? Mommy and Daddy got them some good gear for Christmas. Because they can put a tight pattern together, but their process, the way they're doing it, is off. Now, we know as marksmen, or you may realize this, but what appears to be precision can be process as well. It's not as clear cut as we're making it out to be. But let's assume that you as the operator, you as the marks person, is making that same exact setup and shot. You've got good breath control, you've got muscle memory and good movement and everything in place. Like you're a sniper, you've been practicing this shot for years, you've got it down, and you get a nice tight pattern because you've got a good piece of equipment. But your process, even though you've done it over and over and over again, is not correct. And so no matter how hard you try, no matter how much good gear you get, you're going to get a tighter and tighter and tighter pattern, but you're not going to hit the bullseye because you're doing something fundamentally wrong. You are taking a measurement and you're not moving it to the 1-inch mark. You're trying to measure it at the end of the ruler with a little nubby end that's chipped away. It doesn't matter how precise you get. If you get a ruler that's marked out to the thousandth place and the edge is still broken, you're still going to end up with a bad answer. It's going to be very precise. You're going to get the same answer over and over and over again, but it's going to be wrong. That's what this indicates. Okay? You're getting the same answer, but it's not right. But you've got good gear, so you've got a nice tight pattern. This one is accurate but not precise. How can I say that that one is accurate? Go ahead.
They were all within the blue ring.
Well, they're all within the blue ring, and if I look at where's the center of mass of my hits? The center of mass here of my hits puts me probably right about there, which is in the bullseye. The average shot of those four, there's four of them, right? Yeah. The average shot on those four, no one of those shots is accurate, but the average of them all is accurate. But my pattern is really wide. See? Because my pattern is wide, I'm not precise, even though my average is a bullseye. And here's the deal. None of these is a bullseye, but the average is a bullseye. We'll get into how we use that in science in a minute. Now, if I took this same person, the argument that we're making here today would be if I took that same person and I gave them better gear, what would happen? Go ahead.
They'd be both accurate.
They would be both, correct. With better gear, their pattern would come in tighter. Their pattern would come in tighter and would be at the center of mass of their average. Their average is here. So their pattern would be tight right there if they had better gear. This is a good marksman whose mommy and daddy did not buy them good gear, and they've got to use school issue. Okay? That's what this person is. And at the end, what do we have here? The center mass of their shots is probably somewhere out here. They're not accurate. And their pattern is wide. They're not precise. So this is someone who just showed up and said, hey, can I try that? They're shooting for first time, they're a rookie shooter, and you don't give them the good gear for the rookie shooter, right? You say, here, take the stuff here that's school issue that even our own people don't use, because they're just here to feel the recoil. They're just here to feel what it feels like to let the string slide off their finger or to have that recoil back in their shoulder. They're just trying it out. If they miss, they're not going to be hurt. They're not going to de-learn something. If you're a marksman, you don't take the bad gear. Why? You're going to develop bad habits, bad patterns. So this is a person who's just trying it out. Bad gear, bad form. This one here, good form, bad gear. Here, good gear, bad form. Here, combination of both. Now this is how it affects science. This is actually demonstrating some of the issues we have in science, because precision is an indication of the scale on the measuring device that was used. Here's the deal. Ultimately, precision comes down to bucks. I mean, if I told you that we needed to have some measuring devices for this class, which I did, and I said you needed a ruler, which you do. But let's suppose that I wanted you to be even more precise and said, you're going to need a micrometer for this class. Mommy and Daddy just went from buying it at the dollar store to going to a science wholesaler or a science place online and say, rather than buying a 98-cent ruler, Mr. Baker has us buying a $125 micrometer. What's the deal? Well, the deal is I want you to have much more precise answers. And do you really need us to spend that much money? If you want to be precise, I do. If you don't care about precision, I can let you use a ruler and you can be accurate. Hopefully accurate, but you're not going to be nearly as precise. See the difference? So we talk about precision, we're talking about, it ultimately comes down to how much are we willing to spend to get the kind of answers, the kind of precision that we need, and do we need that much precision? That's how it ultimately plays its way out. So let's say we're looking at a scale and I measure something. The scale on my ruler is to the 1/10 of a centimeter, and I look across and I measure it, and I say it's 3.45 centimeters. Why? My system will measure it to the 10th place, so I need to estimate it out one more to the 100th place. And ultimately, this measurement could be between 3.445 and 3.455. If my length is somewhere in that range, I will see it as this on this system. But if I have an even better piece of gear that measures it out to the, rather than the 10th place, it measures it out to the 100th place, well, then I'm expected to estimate it to the 1000th place. And here's the deal. I'm only estimating between two marks. The more precise my equipment, the more precise I can be in returning with a measurement. And see, my range goes out where it would possibly, if I would see it as a 3.448, it could exist somewhere between this range. And see how fine it's getting. Because of the precision of the instrument, I now have a much smaller range that I'm looking at. And I take it out more and take it out more and take it out more. And that's the difference between using a ruler and using a laser rangefinder. Costs more, but guess what? You get a much more precise answer. And the question is, for what I'm doing, do I need that much precision? And that's the constant battle. How much precision can I afford? So accuracy is operator dependent, and we can improve the results by doing a couple things. Averaging your personal results. Remember that one bullseye, or that one score where they were accurate but not precise? They were kind of broad, and I said, take the average. If you took the average of all their shots, it would be in the bullseye. And that's what we do here. If I need to take a measurement, I can take it one time and live and die by that one measurement. Or, let's say you're on an exercise here in class, and I say you've got 5 minutes to measure the length of this string. And you go measure it one time, right then your answer, go, oh, that was easy. Done. Now I've got 4 minutes and 45 seconds to just hang out. Okay. Or you could take the measurement 20 times. Use all 5 minutes, measure it 20 times, average your answers together, and I would argue you'd have a much more accurate answer. because the average of your answers is going to be more accurate than any one of your answers. In the same way, if you work in groups, if I put you in your teams and you go over to do the same exercise, every one of you does it 20 times, and then you take the average of all 60 of your measurements if you're a group of 3. That answer is going to be more accurate than any one individual's average, which is going to be more accurate than any one individual's one-time measurement. So you can increase your accuracy because the accuracy is wrong because of you, the person. And the way you get a better answer is by using averages, averaging your answers or averaging your group's answers. And precision, it's the instrument. How do you get more precise? You spend the bucks to get something that's more precise, not more accurate. Because if I have a marksman's rifle and I hold it wrong, I'm not going to hit the target. Okay? So just because you have good gear doesn't mean you're going to be more accurate. You'll do it wrong better, but you're not going to hit the target. So we're just a couple minutes from the end, aren't we? So when we're finding out, determining the measure's accuracy, compare the measure to the correct value. And determining the measure's precision, we're going to note the number of significant figures that are in the measure. We are now at the point of talking about significant figures, and frankly, significant figures is too important for us to kind of cram into the next 3 minutes. Correct me if I'm wrong, but we do end in 3. Okay. So I just want to remind you then, let me fast forward to what I have up here in terms of, don't worry about this. We'll go through this tomorrow. I'll leave that on the board for you in your last few minutes to make sure you understand it. And you're dismissed from the bell.